We've looked at both of our alkene addition mechanisms. So now we're ready to actually do some practice problems where we need to figure out which mechanism is going to occur. The way that we're going to do that is by looking at our reactants. We're always going to be starting with an alkene of some sort, but we're going to be adding either hydrohalogenation, which will be using some kind of acid with a halogen, either chlorine, bromine, or iodine. So hydrochloric, hydrobromic, hydroiodic acids. We can also use acid catalyzed hydration, which will be H2O with H2SO4. You might also see this as just H2O. It's going to work the same way, but in general practice, we would use the acid catalyzation to make this reaction proceed much more quickly. Then, in the three-membered ring, you might see halogenation, which you'd be able to identify by it only being reacted with a halogen. We would have to react this in some kind of solvent that isn't going to participate in hydrogen binding, so we would probably use something like dichloromethane. Halohydrogen formation, you're going to see that based on having a halogen in a water solvent. So these are 4 types of reactions that we're actually going to be seeing, and they're very easy to identify just based on what's reacting. Once you can identify that, you'll know, 1, what the mechanism looks like, and 2, what products you're going to have. Because in the carbocation pathway, we're always going to be following Markovnikov addition. We're always going to be keeping in mind hydride and methyl shift possibilities, and we're not going to have any specific stereochemistry. So we don't even need to use dashes or wedges when we're looking at carbocation pathways because it's not ambiguous. The three-membered ring, however, we are going to use Markovnikov addition when we're doing a halohydrogen formation. We are always going to have the anti-conformation in our products, so we always need to keep that stereochemistry labeled either forward and backward or backward and forward. And we are not going to have to pay attention to any hydride or methyl shifts because all of this will occur through that three-membered ring where the carbons are going to be locked in place together. So let's take a look at some examples. The first reaction we're going to look at is an alkene reacting with hydrobromic acid. Our first step is going to be the pi bond of the alkene, doing a nucleophilic attack on the hydrogen. That hydrogen will give up its bond with the bromine, and we can move on to our next step. Our hydrogen is going to attach to the carbon that has more hydrogen substituents, which is going to be our carbon on the end. That's going to leave our carbocation as a secondary substitution, but it's going to be right next to a carbon that is tertiary substituted. So we're going to see a hydride shift before that bromine has the chance to attack. So we're going to have a little hydrogen here. Let's just draw him in. And that is going to be moving onto that carbon. Notice my arrow is drawing from the bond, not from the hydrogen. So after my hydride shift, my carbocation is now tertiary substituted, and my bromine is going to attack that. This will give me my final product with a bromo, 1, 2, 3, 4, butane with a methyl group. So 2-methyl, 2-bromo, butane. Here I have a cyclohexene that is going to be reacted with iodine in the presence of water. So my mechanism is going to be the three-membered ring, and we can start drawing that out with the alkene here attacking the iodine. So the next reaction I'm going to do is a cyclohexene that is going to be reacted with iodine in the presence of water. The first thing that's going to happen is my pi bond is going to do a nucleophilic attack on the iodine. So I've got my three-membered ring set up here, and due to the presence of water, this negative iodide will be carried away by hydrogen binding. This oxygen, however, will still be attracted to the partial positivity on these carbon bonds, and we're going to see it attack. In our final step, I'm going to have one of the hydrogens of this water molecule pulled away by another water molecule. So here I've got my final product, which is going to be an iodocyclohexanol. I can write that in, but one thing I need to keep in mind. It was pretty arbitrary whether this iodine was going to go back into the board or forward. It was just a off-the-cuff decision to do dashes instead of wedges. So in reality, I could have done wedges, and then my alcohol would have been on a dash. I'm going to have a mixture of anti-stereochemistry. So I need to draw both of those possible products. You'll just need to remember that that is the case. In our next example, I have a propene that is going to be attacking a bromine. So the first thing that's going to happen, this is going to occur via halogenation. So my pi bond is going to do a nucleophilic attack onto one of these bromines. That bromine then gives up its bond with the other bromine, resulting in a bromide anion. Now, going into this, we know that my bromine could have attached forward or backwards. It's not necessary to show it both ways. I only need to show it one way just to prove out the mechanism. Once my bromide is here, negatively charged, it is going to be attracted to the partial positive charges on these carbons. It's going to attack the one that is more substituted, which for a final product won't make a difference in its arrangement, but it is still correct when we're drawing out the mechanism that this bromine is going to attack that carbon, because this carbon is better able to stabilize that partial positive charge. So our final product gives us 2 bromo, should be 1,2-dibromopropane. And then drawing in my final product, I draw both of my possible stereochemistries, and my answer is complete. For our last example, I see that I'm going to have acid catalyzed hydration. In this mechanism, I'm going to start with a hydronium ion. I do not need to draw the sulfuric acid resulting in a hydronium ion, and once it does, once that sulfuric acid deprotonates, it's just going to be a bisulfate anion, which is going to be a spectator. So we do not need to worry about that. We're just going to be working with that hydronium. The first thing that happens is this pi bond does a nucleophilic attack onto one of the hydrogens. That hydrogen will then give up its bond to the oxygen. In the next step, my hydrogen attached to the carbon that had more hydrogens attached to it and resulted in a carbocation that is tertiary substituted. Now, this is the most stable possible carbocation, so we are not going to have any hydride or methyl shifts. It's going to stay just as it is. That oxygen, however, is going to be attracted to that carbocation and is going to do a nucleophilic attack on it. Finally, we are still in a water solvent. So my water molecules that are around this molecule, around this alkane, this alcohol, are going to try and grab one of those hydrogens, doing a little acid-base chemistry. That hydrogen then gives up its bond with the oxygen, and we get our final products. In our final product, we have our hydronium regenerated, and we have an alcohol created, removing that double bond. We are going to have this occurring due to Markovnikov addition, and we are not paying attention to the stereochemistry because we're going to have syn and anti-products, and we have no need to draw that stereochemistry out. So we're only going to draw that one product. And there is our final addition reaction.